Hello, this is another video for a design video, and in this video we are going to design a simple power supply unit for an embedded device. So it's a side project I'm working on, and I thought it's wise to just record my thought process and design process as I design specifically the power supply section for this device. So I'll just briefly show you what I have. Um, so far, just so that you understand where I'm coming from before we get to that power supply point. So this is done in KiCad, as you can see, and I've made it to be a hierarchical design. So basically, we have divided different schematics or different sections into different schematics. It's an irrigation manager for just to test the functionality. This is actually a classic project. I think almost everyone has done this at some point. So I have a CPU section here that has a basic MCU. This is a Atomica 2560. Um, we have an Atomica 82 programming chip here. I'll be programming it through USB-B micro. I have a supply for the 3.3 for the 5 volt um, devices for the CPU section. Next, some other part I have is the flash memory, for example, for storage of files, SD card module for large file storage, obviously, and then we have RTC module DS1307Z for timekeeping purposes. Okay, so the other thing I have is output control. Basically, these are just a bunch of relays, low power relays that are being pulsed from the Atmega CPU. Then we can control things like solenoids and water pumps, etc. So I have a bunch of them, uh, around eight of them, eight relays. Then next, what I have is Wi-Fi and comms. This is an ESP32, um, ESP32 S3 Room 1. It's a basic ESP32 device, but it's capable of connecting to the Wi-Fi, so that's why I used it. So data is going to be coming from the at Mega 2560 through the UART channels, and then it's going to be published to the whichever endpoints that I built for it. A bunch of supporting capacitors here, programming method, etc. So all this information is available on the datasheet for further reference. The other thing I have is sensors. So these are a bunch of soil moisture sensors with OPAP comparators, etc. Then we have a BME280 for humidity sensing, flow meter connection. I have like one, two, three, four, five, six of them. This schematic is not complete. I think I should add some more sensors like light sensors and etc. Oxygen measurement, etc. Okay, so now the next thing that we design is the power supply. So this schematic is empty at this point, but for this device, since it's basic enough, I will just brainstorm before I draw the schematic. Let me open let me open Paint really quick and just show what I'm thinking or what should be the power supply. So basically, if this device is going to be used on a farm, it means that we have to have options for the power. So the farm can have electricity supply, like grid supply, 240 it's AC. So if it has 240 AC, then it means that we can have an input here of live and neutral. You can get this from a plug to 40 AC. And then what we need to do, this device is a DC device, so we need to rectify this uh, um, supply from AC to DC. And I want to have 24 volts AC DC that has approximately 1 amp of current for the solenoids. So you realize I showed you the solenoids. So solenoids have an inrush current which I have to supply. So approximately 1 amp. I'm not going to be using very heavy solenoids, but then there has to be 24. 24. It has to be 24 volts DC, right? Okay, so from 24 volts, what happens next? We step it down to different voltage levels. So what I need here is I need 12 volts, I need 9 volts. I can use 9 or uh, let me use 12, then 5 volts, then 3.3 volts. Yeah, 3.3. I think that these are enough for everything I need. So it means for high efficiency from 24 to 12, that's a half of the voltage, which means we need high efficiency supply. I mean devices. So I'll be using an SMPS device here, basically the LM2596 chip or device for this purpose. 2596. Okay, and then this will give me 12. This will give me 12 volts. And then from there, I can also get this another one here and give me 5 volts at this point. So this is still LM2596, but at this point this is 5 volts. Right, 5 volts. And then 3.3, I don't need an LM2596, I can use a LDO for that. So which means I can get this 5 from this point. Oops, I can get 5 here and drop it to this is an LDO. So most popular, there are many other devices, you can change this during the design, but MS1117 3.3, right? MS1117 3.3, right? So at this point we have 3.3. So we have handled all those 3 voltages. Now this is from the grid, right? What if someone does not have grid directly and they want to connect let's say a 12 volt battery, right? Or they don't want to connect it directly like this, you see, like that, but they want to have, they have an adapter. You can provide an adapter for that, a 12 volts adapter. So it's still coming from the grid, but they are, being safe or staying safe with the supply. So which means that I need a 12 volts barrel jack. So the way I like to think about my designs is that provide, if cost is not a problem, provide what you can and then modify later based on what you find out. Right, so that's why I'm providing an AC and a DC supply directly. So I'm rectifying on board, and then this part I'm providing an already rectified and step down supply. Right, so this is 12 volts from a DC jack. This is a DC jack here. DC jack. DC jack. Right. So from a DC jack, you realize that this is 12 volts. LM2596 expects an input V in to be plus 1.5 or 2 volts, I think. So you can't get 12 and get, you can't input 12 and get 12. You can only input 13.5 and up, or 14 or 15 and up to get 12. So this is not a pass-through device. So what I'll do to reuse this component, I'll get this jack to this point so that I get 12 volts here. Okay, then I get 5 volts and 3.3. So you realize that if I use this configuration, I still get my 12, 5, and 3.3 volts. Right. So this device also is called the LM2596. Okay. Now, if you look at this circuit, it's fine, but there are some missing things. Literally, if you take it to the field, it will work, yes, but you can improve it. So how can we improve it? First of all, so if you're using AC, the first thing you should do is do a voltage and overcurrent protection. So we can have a fuse at this point, right? A simple fuse, maybe 5 amps fuse, or 13 amps, depending on the needed supply current. Then we can have another thing, a line to line protection. You can have an MOV here, metal oxide varistor. So let's write MOV, is not visible. So let me write MOV. What color is visible? Oh, okay, that's visible. It's better. So MOV, okay, protection. Right. What I'll do, I'll draw it down here. Colors, colors, colors. Okay, so this is a fuse. Fuse is like this. Then we have an MOV. What's the symbol for an MOV? Okay, an MOV looks like this. Something like that. I'm not sure. Yeah, like that. And then this is the next line. So this is live. Obviously, the fuse is connected to live. Then neutral is here. I don't necessarily need the earth. Can or cannot be there. Not a must, but yeah. So that's one thing we can do for the AC. I don't want to go into complex design, just want it to be simple. And for the DC, what you can do is reverse protection. For example, someone might connect their battery negative to positive and positive to negative. Reverse protection, number one. Number two, you can have what we call over voltage or OVP, over voltage. So if on a rare case that this thing goes to 15 volts and you don't want your device to take in 15 volts, you can shut off. You can actually shut off this part. This part. So there are ICs for that, or you can use MOSFETs, but I'll use an IC for that. Okay, so I hope this is simple enough and clear enough. There is still some more improvements, but let's start with this for now. Right. Okay, let's do that. Good. So let's start with the AC supply. So for the AC, what I'm planning to design is that the user can, or rather when I'm installing it, I can use screw holes here to screw the two AC wires through a connector on the board, onto the board. Okay, so I'll add screw terminals. This thing takes a minute or two. Anyway, meanwhile, other things we can do obviously is to have indicators for power. Oops, excuse the drawing, but I'm just thinking as I go. So this is just a simple LED for the power. You can have one here, you can have one here. Then you can have test points to test these power supplies or power voltage outputs after so you have turned this device on. So this is test point. Test point. Now, one question that you might ask is, you think about the worst case scenario. What happens if a user needs to select that they have reliable grid, they don't need to use 12 volts, or they have 12 volts and they don't need to use the light. So what you can do for that, you can have desolderable jumpers, right? So you can have desolderable jumpers here, like a 0 ohm resistor you can remove, and another 0 ohm resistor here that you can remove. Actually, let's have it here for the AC, so that this power does not flow this way, right? When you remove this, does not flow, to this converter, right? That, okay. Okay, so these are jumpers. Okay. Jumper. They can be solderable or they can be header pins, right? Mhm. Just a minute, let me close this part. Right. So this 5 volt 3.3, they all go to the components, obviously. Go to the components. Okay. Uh-huh. So looking at it, I think this is good enough. Now for this part, let's see what components you are going to use. So for this part, we should use a compact module for that purpose. There is the most common, the high link one, I think. First. For example, this is Shenzhen high link 10 watts. You see, this is now 10 watts. Output is, if you look closely here, output is 5 volts, 2 amps, which is not useful. For my case, I need 24 volts, uh, approximately 1 amp. Basically, high link, most of their devices are for low powered applications, 10 watts and below, you know. But we will look for another. We will look for another. Okay, now you see this table, for example. This is HLK 10M24, so 10 watts, 24 volts, but the current is 0.4 amps. See, so the more the voltage goes up, the less the current comes down, basically, to maintain the power. See, to maintain the 10 watts output power. right? Uh, but there's another manufacturer called Inwell. So this guy, these people, these guys manufacture high quality, high voltage um, power converters. So this keycard is done. Alright, cool. So we can start our design. So the first thing we add is screw terminal. So right now we are designing the schematic. We don't wanna put into mind a lot of footprints and whatnot. For screw terminal, you need two pins. Okay. So place that. R for rotate. Uh, so this is what this is the AC in. AC in. Okay, from AC in, I need a fuse. So a fuse is always placed before the varistor. Fuse. Then we need a varistor here that can handle up to 240 volts. There's a rule that says you're designing for 240 volts, use a component that can handle plus 10% of that. Some designs use up to 50%. So if you're designing for 240, you can use up to 300 or 400 volts of voltage connection. Right, so varistor, this is a component, and then we connect like that, connect like that, connect that way. Right, we'll come back to label the component sizes and values, but meanwhile you can label the net. So L for net, and then this is live view. Okay, live view, and then this other guy here is neutral in. Place it right there. Okay, now we say from this point we go to a converter, this rectifier. So I'm not sure that this symbol is in keycard, but let me check. Let's check and see whether it's the power module. Power module. Okay. Yeah, they see. There you have there. Good. They're there. 24 volts for 17 milliamps. These are HLM. 10 watts. These are small. Anyway, what I'll do, I'll use this symbol, but then we will change the footprint later when we are designing the PCB. But let's check a little bit. We might be lucky. IRM, I want a 24 volts. Oh, okay. 24 volts, 900 milliamps. IRM 2024. The next thing we can do is check whether it's available on JLC, LCSC. IRM 2024. I think I have already searched it. Yeah, it's the IRM 2024. So it's right there. So KiCad has that. So we can get lucky. You can use this directly like that. Good. So connect that way. Connect this way. All right. So right here now we get our ground. So this is ground. Get ground. This is 24 volts. So 20, 24. Okay. Not sure if this guy is on 24 volts. Right, it's there. 24 volts. Okay. 24 volts. Next is LM2596. Right. So from this point we convert it. Now there are different ways to do that. It's not a must use LM2496. Texas Instruments have a tool called the WeBench Power Design tool. Let's open it and use it to design this circuit. So WeBench Power Designer, click on this part. I'll show you this way, and then there's another way to choose components for the LM2596. So this is DC start design. So input is 24 volts, right? So supply type is DC input. Let's say minimum is 23 and maximum is 25. And then typical can be 24, right? We expect an output of 12. So output of 12 volts at 2 amps. We cannot have 2 amps because this is already 1 amp. So I'll use is it? I'll use 1 amp here. It's not, I don't want it to be isolated at this point. I want my design to be balanced. I agree. View designs. Let's wait for that. As it's generating, you can open the datasheet for LM2596. 2596. Back converter datasheet from Texas Instrument. Open this. Um, so you open that. Good. So you can see now we have these designs. Yeah. So you can choose whichever you want and customize it. TPS 40 54 22. Okay, LM 25011. All these designs are there. Okay, so efficiency, check the efficiency. Actually, the efficiency is always very important. 90, this is 95 almost. Cost, okay, whatever. As much as these are important, most of them, or the cost, I want the output to be 12. So that's one. This is another one, 1.26, 2.52. Okay, let's go with the first one. TPS what? TPS 5430. So I'll choose that. Almost all of them are the same, like same efficiency. So I click on this. Then the next thing you do is you check whether this component is available for purchase. So this is TPS 5438. TPS 5438. TPS 5438. Is that it? TPS 5438. DDC. Yeah. Sorry. Okay, cool. So yeah, it's there, $0.9. Okay. Step down type adjustable 3 amps, 4.5 yeah, converter, DC backup. Let's go with that. So what's the package type? First of all, do we even have the symbol for this keycard? If you're using EZDA, it's easy actually, because you just pull in that symbol and get the symbol in EZDA very fast. But for keycard, you have to check the footprint. This footprint is SOT236. That will come in handy for during the PCB design. So yes, SOT236. Next, let's try to look for it here. I'm not sure it exists. So when you press A, you open this component manager or component placement for keycard. TPS 5438. TPS 54. It's not there. So let's see. You can choose another device with the same pins, or you can create a symbol. It is TPS 5438, right? This is it. SOT236. Good. Just right here. Okay. So next is we follow now there. We follow the WeBench. Okay, so they have a 2.2 microfarad capacitor at the V-in pin, obviously to filter. So I'll try to rush here a little bit. So what I'll do, press A. The speed is also limited by the speed of the computer. Yeah, it's a problem. Let's see. Small. Place a capacitor. Press start, escape. Place a wire here. Place a wire. Ground. Place. This is 2.2 microfarad. Is it 2.2? Yeah, 2.2 UF. It's 2.2 UF. Okay, 2.2 UF. Next, 100 NF on the boot pin to the switch pin. So I'll copy this. R for rotate, boot to this guy the switch. This is 100 added NF. Okay, and then next thing is 22 microfarad inductor. So here we look for an inductor. Inductor. Okay. Rotate. Place it right there. Press escape to avoid placing repeated components. So this is 22 microhenry. It's supposed to be 22 microhenry. Is it? Yeah, 22 microhenry. You have feedback resistors here. One is 100 kilo ohms, the other one is 5.23 feedback resistors. So place R underscore small. So this is a symbol I prefer for resistors in keycard. That's why I'm using it. There's another one for the US symbol, but basically someone uses what they prefer. So I'll copy this ground and place it right here. Then these pins are used for setting the output voltage, the feedback pins. This is 100 kilo ohms and 5.23. So this is 100K. I'll use a 0.005. So I just write it here to remember when I'm uh, building the PCB. 8.23, I hope. And C out of 4.7 um, microfarad, quantity of 5, 1 million. Okay, let's see the BOM. Okay, so they want, I think they want us to place this 5 of them in parallel. We'll check the data sheet later, but for now, let's place 5 of them. Not sure why, but maybe I'm actually, I think I'm wrong, but good thing is we can confirm. So instead of doing this, I can just save this microfarad, delete this, copy, paste, 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 paste them right there. So I prefer to have grounds, different grounds. Okay, connect, connect. I'm not sure this is right, but yeah, we always find out. We can always find out. Okay, so go back to WeBench, and I think that's all. V in is right there. Yeah, yeah. But move on to the next thing. So what's remaining here is ground. Enable pin by default. What I know is that if you tie it to VCC, it enables the chip. But what we can do is go to the part number. Where is it? This, and open the datasheet. Okay. Open the datasheet. So even the datasheet is telling you to create a custom design using the WeBench Power Design tool. Okay. What was I checking? Checking the EN pin. This pin is the enable pin. Float the EN pin to enable. Okay. This is different. Floated to enable, so it will remain floated and connected. That's why the datasheet is always important. Plus, the WeBench has of course told us I did not trust it. That's why I had to check. Yeah. Okay. Okay. Anyway, yeah. So what I'll do, I'll put a text here that says to do check output capacitors. Check output capacitors. Um, for yeah, four is too large. Two. Yeah. Check. Doing design review. All right, cool. So the next thing we have is we have got 12. We need 5. Right. Okay, so we have this design here, TPS 62932 chip that we have to transfer to picard. So I have the part manager open and I'll place TP. It's TP what? TPS 62932 to TPS 63932 TPS 63. Let's see. TPS 6293. Yeah, 62. This is it. So KiCad is right here. So remember we have 24, so we want we have 24, we have 12, we want 5 volts at this point. So this design is going to give us 5 volts output. Let me just confirm that first. Yeah, output 5 volts at 2 amps. Okay, so the circuit again. Let me open the circuit and here it is. So we need a capacitor, 10 microfarad capacitor. I'll copy this guy here, paste. We need 100 NF, we need 33 NF, right? So this is 100 NF. This is 10 microfarads. The other one is 100 NF, right? Then the other one is 33 NF. 33 NF. Alright, cool. So ground copy, paste. So paste here, paste right here, and paste right here. And connect all of this to V in. Connect to V in, connect to V in. And then EN is unconnected and RT is unconnected. SS is connected to 3. It's connected to this pin. This goes there. Output you have 100 NF. So R for rotate between the PST and the inductor. So I just wire those directly like that. Then you have two resistors here, 52.3 and 10K. So I'll just copy these two, paste. These ones go to feedback. Ground is right here. Then these two go to an inductor. The top goes to an inductor. So I'll copy this guy and then place it right here. Wire it. This is 10 microfarad. Remember, this should be able to handle 10 microhenries. Sorry, this should be able to handle 3 amps or at least 1 amp because the module we have is 1 amp rated. This is 52.3. 52.3. This is 10K. 10K. Alright, cool. Then we have an output capacitor of 47 microfarad. So place it right there. So I'm moving as fast as I can here so that I think we have done most of these parts on the upper design. 47 microfarad. Cool. So this is supposed to be 5 volts. So I'll place a 5 volts symbol here. Um, 5 volts plus 5V. Okay, cool. The next thing we have is we need is 3.3 volts. So we can use a TPS. So let's search on KiCad directly first. So we can look for 3.3 volts LDO regulator. Doesn't have to be LDO. Let's just look for regulator. I want to use a Texas Instrument one. So there's a TPS series. There's a DLM, LV, LT, TLV. I'm looking for this guys TLV 75. Let me use this TPS. I mean TLV. This one takes in 5 volts. Um, and output 3.3 volts. So you can look for the data sheet for this guy. Proceed, paste it here. Look for LCSC. Okay, meanwhile, can be placing capacitors because I know they need capacitors. One, another one here. Okay, then we place ground, connect here. Then what we have here is 3.3 volts. So this should be plus 3P3. Plus 3P3. Plus 3.3. Place it right there. We'll check the data sheet later for this. The next thing we design now is the DC. So remember, this is taking source input from 24 volts. So 24 volts here. Good. So then let's place barrel jack. So DC barrel jack upper. Yep. Then paste it. Ground. Replace reverse protection. Use a shortcut diode. This thing is slow. Then we need to do things something like our voltage protection at this point. So there's a chip for that. It's called LTC 63 something. Let me look for it. LTC 63. Yeah, so it's called the LTC 4365. 365. So I want the one that is TSO 810 that can be soldered by hand. So this chip basically is an overvoltage protection IC and under voltage and also reverse protection, right? So V in is right here. So let's open the data sheet and see what is needed to be done for LTC 43 60 60 what 65 43 65, yeah, 43 65. Right here, open the data sheet. Okay, so I'll use this exact circuit right here. I don't need to change anything. I want mine to be 18 volts of voltage and then 3.5 volts under voltage. Then what it does, it just outputs a pulse here that cuts off V out from V in, right? Yeah, so I need these two MOSFETs, SI 4946. So let's look for that or something close to that. SI 4946. It's not there, so but we have other MOSFETs and MOSFETs and channel, trench FET and channel, which is okay. Also can use this dual, right? So R for rotate, unit A and B, right? So connect that, and connect that. Then this is connected to V in, if I'm not wrong. Yep, and then V out is connected right there. So V out is here. Ground obviously is grounded. Ground. Okay, so the next thing is under and lower voltage. We have 510K, 1, 2, 3, 4 resistors. So let's place them. Copy this and paste here. Paste one more and one more. This is 510K, 5, 10. It's connected between V in and SHDM. So it's connected right here and here. Okay. Then this is 1820K. This is 1820K. 1820K. We have 243K. 243K. Then we have 59K. 59K. Okay. Connect them. Connect like that. Copy. Paste here. Just rearrange a little bit. Then the next thing is under voltage or voltage. So right here is under voltage. I mean our voltage. This point A is the under voltage. Then this top goes to V in. This goes right there. Alright, cool. So fault is not being used. So I can just put a not connected flag at that point. So right here, this is 12 volts DC here. So I'll place a net. No, yeah, net. Let's say 12 volts DC. So now, remember we said that we want to choose between AC and DC and have jumpers to connect that. So once we get 12 volts, we can pass it to this SMPS and then convert it to 5 and 3.3. So what that means is that we need to connect this part with this part right there like that. But we also need to have like a way of enabling. So what I'll do, I'll add simple jumpers here. Uh, I'll use jumpers to be right here and right here. So this is called DC enable, and this is DC enable. Okay, so I'll confirm this circuit. So to do is confirm. Okay, confirm. Okay, right, cool. That's nice. What else should we add? We have 3.3. We have 5. We have 12 DC. All right. So maybe the other bunch of things are like LED indicators and yeah, mostly LED indicators. But I think at this point, this schematic is done. 24, 12, 5, and 3.3. And I way to select. Other things you can think of are like solar panel connection, but I don't want to think about it at this point. So yeah, and that's that. And see you in the next one.